Unit 10, Gas Laws. Our first objective, describe and understand the kinetic molecular theory of gases. The kinetic molecular theory of ideal gases has 4 parts to it. Number 1, gases consist of large number of molecules that are in constant random motion. Number 2, the volume of all molecules of the gas is insignificant compared to the total volume in which the gas is contained, meaning gas volumes don't matter, they take on the volume of the containers in which they are held. Number 3, attractive and repulsive forces between gas molecules are insignificant. And then number 4, collisions between molecules are perfectly elastic, there's no loss of energy. So let's kind of break these down a little bit. Number 1 is true all the time for both an ideal gas, gases that behave perfectly theoretically the way that we expect them to, and for real gases, real life gases out in the real world. Number 2 is this rule is true only for an ideal gas, an imaginary gas that follows all 4 of these assumptions all the time in theory, right? Real gas particles do actually take up space themselves, but because they're so far apart from each other, that space is negligible and we don't worry about it. Number 3 is going to be true only for an ideal gas as well, because real gas particles do have forces of attraction and repulsion. So number 2 and number 3 really are only of concern or come into play at really low temperatures or really high pressures, where particles of gases are moving slow enough to interact with one another and are close in proximity to each other to interact with one another. And number 4 is going to only be true for an ideal gas. Real gas particles do lose energy due to friction, but all 3 of these things that are red and in boxes are going to be considered negligible in general, which is why we tend to just follow these rules for and consider all gases in an ideal state. There are 4 variables that are going to describe a gas: volume, or the amount of space the gas takes up in milliliters or liters; 2, pressure, which can be in one of the following units: atmospheres, millimeters of mercury, kilopascals, and torr. In the United States, you might be familiar with pressure in PSI, pounds per square inch, like in a car tire. Number 3, temperature is going to be in Celsius or Kelvin. And number 4, the number of moles, which is going to be the amount of the gas that we may be dealing with. But we're going to save moles for later, and we're going to focus on the first 3 for now. So STP, you're going to see often, you have seen up until now, that stands for standard temperature and pressure. And from now going forward, you're going to be asked to memorize standard temperature and standard pressure. So it's the conditions of standard temperature and pressure. Standard pressure is going to be 1 atmosphere of pressure, which, if you express that in one of the other units, 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 760 torr, which is also the same as 101.3 kilopascals. So the standard temperature is going to be 0 degrees Celsius, and what we'll come to learn is also 273 Kelvin. STP allows scientists a consistent set of conditions to compare volumes of gases to each other. So temperature is a measure of the kinetic energy of the motion of particles. Particles at higher temperatures move faster and with more energy. Particles at lower temperatures move slower and with less energy. So if we take a look at this, here we have 8 Kelvin as the temperature, and so you can see how very slowly the particles are moving. They have a low energy and they move slowly. Over here on the right, 837 Kelvin, a much higher temperature, and you can see the particles have a lot higher energy and they are all moving a lot faster. So now we're going to practice converting between Celsius and Kelvin. To convert Celsius to Kelvin, we have this equation. Kelvin is equal to your temperature in Celsius plus 273 added to it. So if we look at the first one, 17 degrees Celsius is how many Kelvin? I'll take 17 degrees Celsius, I will add 273, and then I'll have my temperature in Kelvin, which this one will be 290. My second temperature, 55 degrees Celsius, if I want to change that to Kelvin, then I would take 55 and I would add 273, and that would give me my Kelvin temperature, 328. Finally, if we want to do the reverse, take Kelvin and turn it back into Celsius, we'll just do the opposite. We'll take the Kelvin temperature, 250, and this time subtract 273, and then that answer is my answer in Celsius, in this case, negative 23 degrees Celsius. To recap, if you want to change Celsius to Kelvin, you take your Celsius temperature, add 273. If you want to change Kelvin to Celsius, you take your Kelvin temperature and subtract 273. Pressure is a force exerted by a gas per unit of area. Pressure results from the collisions of gas particles with the walls of the container. Let's consider this simulation. I'm going to add some gas into the container, and you'll notice here that they exert a certain pressure, 23.4 atmospheres. Over here measures wall collisions. Every time the gas particle collides into the wall of the container, that measures as pressure. So if we were to see how many collisions are occurring in the course of 10 picoseconds, we have 172 wall collisions. Now, if I were to say add some more gas, 1, 2, 3, 4, well, now we can see that the pressure is at 46.7 atmospheres, almost twice as much. And so now how many wall collisions are occurring? And we're at 394, also almost twice as many wall collisions. There are other things you can do to increase the number of collisions with the wall of the container. For example, if we were to heat up the gas particles inside of this container, what would you expect? You would expect the particles to move faster, and if they're moving faster, then will they collide with the walls of the container more often? And we can see our pressure gauge is increasing. Let's see how many wall collisions are happening now that I've heated up the gas. We had 140, and now we're up to 254. So that's because they're moving faster and they're hitting the walls of the container more often. If I were to spread the container, make a larger container, what's that going to do to the number of collisions with the wall? So now there's more space. Are they hitting the wall more often or less often? Let's see. It was 254, and now it's at 213. So why are they hitting the wall less often? Well, they have farther to travel, and so they're going to collide with the wall's containers less often because they have to travel further in order to hit the wall of the container. So the more collisions with the container walls, the higher pressure there is inside of that container. As a real-life example, air pressure, which is the pressure that the atmosphere is bearing down on top of us, exists. Air pressure is all around us. There is more air pressure at sea level, which is lower down in the atmosphere, and less air pressure the higher you are in the atmosphere, so like where a plane flies. And then as you move on out into space, then there ends up being zero air pressure once you get beyond the atmosphere. So to determine the pressure of a gas, think about the number of collisions that take place and the force of those collisions. The more collisions or more forceful collisions with the container walls, the higher the pressure. The fewer the collisions or less forceful collisions, the lower the pressure in the container. So now let's explore what the effects are on each of the following on pressure and why those happen. First on our list is if you double the amount of gas particles, how does that affect the pressure? So here I've put 4 pumps of gas, and now I'm going to add 4 more, double the amount. And what we've noticed is that the pressure doubled. So that would be your answer to number 1. If you double the amount of gas, you're going to double the pressure. Okay, what if we were to reduce the amount of gas by half? So here I put 4 pumps of gas, and we have a pressure of 23.4 atmospheres. Now I'm not going to be able to do this exactly, but I'm basically going to try to let about half of the gas escape out of the container by opening the lid at the top. And so as we watch where roughly half of the gas escapes the container, we can see that what happens to the pressure is that it cuts down by half. So if you reduce the amount of gas by half, you reduce the pressure by half as well. Number 3, if we triple the temperature. So let me go back to this reset place here. All right, here's the pressure, 23.4. What happens if you triple the temperature? And so the temperature is at 300. Let's bring that temperature up to 900. So we have 898. The pressure was 23.4, and now it's nearly 70. which is going to be just about triple. So if you triple the temperature, you triple the pressure. All right, what if we reduce the pressure by 1/3? So I will reset. I will put 4 pumps of gas, and now we have 300 Kelvin, and I'm going to reduce that by 1/3, pretty close to 200. So it was 23.4. We reduced the temperature by 1/3, and what that did was reduce the pressure by 1/3 also. Okay, now we're going to double the size of the container. So let's make the container about this size, and let's see if I can get the width. 5 nanometers is my width. All right, the pressure right now is 46.7. If I were to double the size of the container, make it 10 nanometers, now the pressure is 23.5. So doubling the size of container caused the pressure to cut down by half. For our final example, because our container can only get this large, I'm only going to be able to show you what happens if I reduce it by 1/3. So notice that the pressure currently is 15.6 atmospheres. If I reduce the container size by 1/3, see there's 1/3 the size of the container, what will happen to the pressure? And the pressure is going to multiply times 3. It was 15 atmospheres, now it's about 46 atmospheres. So just decreasing the volume of the container by 1/3 would cause the pressure to increase by times 3. So can you guess what would happen if I could reduce the size of a container to 1/4? What would happen to the pressure? So now, given all that you've seen, let's consider 2 discussion questions and talk about them in class. In terms of the kinetic molecular theory of gases, how can an increase in temperature of a gas confined in a rigid container cause an increase in the pressure of the gas inside of that container? And then number 2, there's a government warning on all aerosol cans that states, do not store at a temperature above 120 degrees Fahrenheit. Why is this warning required in terms of the relationship between temperature and pressure and the kinetic theory? What could happen if the can were to be heated above 120 degrees Fahrenheit?